Welcome to Lecture 6.4 in Math 1324 on Basic Matrix Operations. Today's brief pause before we begin is all about setting goals. You know, in Alice in Wonderland, she meets the Cheshire Cat and she asks the direction someplace, and he says, well, if you don't know where you're going, then any direction is fine. And that's kind of what life is like without a goal. And, you know, I think back to when I started college and I enrolled in an electrical engineering program because my guidance counselors in high school, when I suggested that I wanted to be a teacher, were pretty persuasive that teaching jobs weren't very well paid. There weren't a lot of teaching jobs at that time, and that because I had real strengths in math and science, that engineering would be a better choice for me because I would be pretty much guaranteed a job, starting out at a good income right out of school, with a whole future in front of me. I didn't realize until about my junior year, and it's amazing to me how naive I was, that I didn't like engineering. I didn't enjoy it. I wasn't passionate about it. And so my classes were a constant struggle to do well in because I didn't have an affinity for it. Even though I may have had some great basic math skills, I really wasn't interested in the theory and the mechanistics, etc., behind electrical engineering. And so I think it's really important to kind of take a step back. And I know that for a lot of you, you're younger, and you may not have the experience to kind of decide where to go. But there's a lot of things you can do on the internet about career assessments, you know, about things that you're interested in that can give you some ideas. And I did those in high school as well. It always makes me laugh because I remember one of the jobs, one of the top 3 jobs was funeral director, and I always thought that was a bit odd. But anyway, so it's very important, I think, to have a plan or a goal, someplace you're heading to. That may change, and that's fine. And I've had a great career, and part of it's because I have that Bachelor's of Science in Electrical Engineering. Most of my corporate jobs were with technical companies. I actually became the marketing director of a company in Munich, Germany, and lived and worked in Germany for a couple years. And it was a technical company, and because I had had that technical background, I could read their documents and then translate them into communications and marketing for the general public. So it did serve me, and so that was a good thing for me. And there's a book called The Alchemist that talks to that, about how often you think you've taken a wrong turn, but maybe that wrong turn is actually giving you skills or knowledge or experience that will later come in handy for you. So maybe there are no wrong turns, they're just delays, etc. The other thing about a goal is working towards it. A lot of times we think of a goal or a dream, and then we can't imagine making it happen. It's too much work. It's too long to get there, etc. I don't know what to do. Well, everything, you know, I mean, even that old saying, the journey of 1,000 miles begins with one step. In most cases, I think you can probably figure out one thing you can do to move forward in the direction of your goal. So, for example, let's say that, you know, one of your life goals is to travel outside of America and you haven't done that. Well, one thing you can do is simply to get a passport, or, you know, pick 5 countries you want to visit, or pick one country you want to visit and learn something about them, maybe learn the language. So there are always things that we can do that help us move forward. And I do believe that there's something about the momentum of taking a step, even if it's a small step, in the direction of your dreams, and a little progress each day adds up to big results. Be the knight of your goal and a warrior of your dream. And you know, this is just speaking to the fact that you know, make sure it's your goal. Don't be fighting for someone else's goal. Be the knight of your own goal. Identify what you really want. don't pursue money, etc. Necessarily. I guess that could be your goal, but it certainly could be part of your goal. But maybe, it's my opinion that if you pursue work just for financial interests, you're probably missing a lot of the things that that really feed you, that you're passionate about, that may not be present there. But once you do have that goal, fight for it. Be a knight of it. Do good things, be of good character, but be willing to progress and work hard and fight hard to reach that goal. You're going to have setbacks. We've already talked about failure in this class, but don't decrease the goal just because you've had a setback. Oh, I can't do that. That's not possible. They say argue for your limitations, and sure enough, they're yours. So instead of decreasing your goal, increase your effort. Maybe you didn't do well in the first test. Maybe you didn't do well, it doesn't mean you can't do math. What are you going to do? What did you do well? What didn't you do well? And change what you're doing or how much you're doing it, so that you can reach your goals. Sometimes you win, sometimes you learn. Again, another kind of thought about failure, and that failure isn't necessarily complete. It's an opportunity to learn, adjust tactics, adjust something that you're doing or how you're doing it. The goal isn't more money. The goal is living your life on your own terms. Now, money may certainly come into it if you're thinking about career choices, but that's not the only choice. And I know a lot of unhappy, wealthy people, and I know some unhappy, poor people too. So, it's just a part of it. Make sure that you're doing something that you feel called to do, that you feel that you would be good at it, and that you would enjoy it. A majority of our lives are now spent in work. So think about that. Find something that maybe gives you the money that you desire, but that's also something you enjoy. Okay, so now let's look at our lecture today. Basic matrix operations. Until now, we've used matrices only as a convenient shorthand to solve systems of equations. However, matrices are also important in the fields of management, natural science, engineering, and social science as a way to organize data, as example 1 demonstrates. Business. The Easy Life Company manufactures sofas and armchairs in 3 models, A, B, and C. The company has regional warehouses in New York, Chicago, and San Francisco. In its August shipment, the company sends 10 Model A sofas, 12 Model B sofas, and 5 Model C sofas, 15 Model A chairs, 20 Model B chairs, and 8 Model C chairs to each warehouse. With the understanding that the numbers in each row refer to the type of furniture, sofa or chair, and the numbers in each column refer to the model A, B, or C, the same information can be given by a matrix as follows. And here you see a 2x3 matrix with sofas in the first row and chairs in the second. The model of furniture, A, B, or C, is the columns, the types of columns. And there you can see our matrix, 10, 12, 5, 15, 20, 8. So there you see it as a table that's described and labeled on the left, and then you see it as matrix, as a matrix titled letter M. Just a quick review and add some more vocabulary. The order of a matrix is its size, which again, remember, is the number of rows by the number of columns. Here we have a 3x4 matrix. We have a, let me pull my pointer up here, 3 rows, 4 columns. Here we have a 3x1 matrix. This is called a column matrix because there's only 1 column. So there's 3 rows, but only 1 column. Here we have a square matrix where the number of rows equals the number of columns. This is a 2x2 matrix, 2 rows and 2 columns. Here we have a row matrix, which is 1 row and 3 columns. And a matrix that consists only of zeros, this is about the members in there, is called a zero matrix. So you can see we have a 2x2 zero matrix on the left, and a 2 by 4 zero matrix on the right. Matrix notation. A matrix is usually named with a capital letter, for example, letter A. Then each element or member is noted as a lowercase letter, in this case lowercase a, with the subscript indicating the row and column. That's very important. Row comes first, just like the order, row by column. Row comes first. So A sub 32 indicates the member or the element in row 3, column 2. Row 3, column 2. And you can see this documented in the matrix at the top with all the subscripts there. You'll notice that all the rows, for the first row, the first digit is 1. And then we have column 1, column 2, column 3 in the second digit. Okay? If you're going down a column, you'll notice all the second digits are the same. For example, in the middle column, we have 222 as the second digit. This is very important notation for homework and the test. For example, we're talking about matrix addition now. Remember the furniture shipments in August, M. That was matrix M. If matrix N represents shipments made in September, how many total shipments of each type of furniture were shipped? So here we're trying to add the number of furniture, each model and type of furniture, and trying to figure out the total shipped. Notice what we're doing here. This is the number of sofas, Model A sofas shipped in August, Model A sofas shipped in September. So the total would be 10 plus 45 equals 55. The number of Model A chairs shipped in August was 15, in September was 65. So totally we have 80, 65 plus 15. So what we're doing in matrix multiplication is simply adding the corresponding elements. So we're adding element M sub 11 plus N sub 11 to get our total shipment of Q11. So what do you think this says about addition requirements for matrix order? For example, if we have a 2 by 2 matrix and we want to add this is 1 row 3 columns, 1 by 3 matrix, what do you think would be the result? There's no solution. In order to add matrices, they have to be the same order. And this is the same for subtraction. See if you can find the sum of each of these matrices. Hit pause and see if you can do these. For problem A, you should get 1, 0, 16, 6. For matrix B, for problem B, you should get no solution. Matrix subtraction is the same as addition. We would simply subtract the same elements. So see if you can do these 3 problems again. Hit pause, do these 3 problems, and then hit play. Just take a few seconds. Here's the answer to problem A. 1 minus a negative 2 is 1 plus 2 or 3, etc. Here's the solution to problem B. 8 minus 3 is 5, etc. I'm not going to go through all the elements. And for C, of course, we get no solution because the matrices are different sizes or different orders. Matrix scalar multiplication. Scalar multiplication is when you scale up or scale down each element in a matrix by multiplying each by a constant. You scale up by multiplying by a positive whole number, or actually a positive number greater than 1. you scale down by multiplying by a fraction. For example, maybe you want half of the order to go, so you would multiply each of the elements by 1/2. For example, to double our shipment, we would double the matrix, which means 2 times A. This is scalar multiplication. Notice it's a capital A, 2A. And we get the answer to that, or the new matrix of 2A, by simply multiplying each element by 2. So if we wanted to double our August shipment, this was our matrix M. Actually, if we wanted, we were having a big time sale, we want to send 6 times as much as we send in August, we would multiply this matrix by 6. So you can see 6 times 10 is 60, 6 times 12 is 72, 6 times 5 is 30, 6 times 15, 90, etc. And so you just multiply each member by whatever the scalar is. Now, inverse matrices can be found by using scalar multiplication and multiplying by -1, okay? For example, the inverse of A is -1 times A, which we denote by -A. So if I wanted the inverse of this matrix, all that's going to happen is everything that's positive is going to become negative, and everything negative is going to become positive. So there are some rules about inverse matrices. Let A and B be any m by n size matrix, and let O be the m by n zero matrix. So this kind of follows the same kind of operations as general math for addition and subtraction. A plus the inverse of B is the same as A minus B. A plus the inverse of A will give me a zero matrix, a matrix with all zeros as members, which is the same thing as A minus A. A plus 0 will give me the same matrix as A, and that doesn't matter if it's A plus 0 or 0 plus A. We've had a relatively short lecture today. Hopefully this helps you, and if you have any questions, reach out.